All right, welcome. What we're going to do here is something pretty ambitious. We're going to map out the entire landscape of computer science. We'll start with the literal sand and silicon that powers our world and climb our way up, layer by layer, all the way to artificial intelligence. Okay, let's jump right in.
So, this is it. This is the big question, isn't it? How do we go from a dumb piece of rock to a machine that can actually think, that can create, that can learn? It's really a journey of abstraction, moving from the physical world of engineering to the pure world of logic, and then finally into this wild territory where systems teach themselves. And that's the exact path we're going to follow.
You know, no matter how complex or abstract the software gets, it all starts right here with the hardware. I mean, everything. Before a single line of code can even exist, there has to be a physical engine ready to run it. And at the very heart of that engine is the CPU, the central processing unit. It's the brain of the whole operation.
Now, when you look at a table like this, it's easy to just see a shopping list. But it's so much more than that. This is really a map of design intent. A Core i3 is literally engineered to handle basic tasks efficiently. A Core 9, on the other hand, is a beast. It's built from the ground up for incredibly complex, parallel jobs like 3D rendering or editing huge 4K video files. The hardware itself is specialized for the kind of problems we want to solve.
And this right here, this is a perfect example of one of the fundamental trade-offs in computer engineering. It's kind of amazing when you think about it. A single letter in the name tells you the entire performance philosophy of the chip. A U means it's all about efficiency, giving you that long battery life. But an H or HX, that's just about unleashing raw, unapologetic power, and you'll pay for it in battery life and heat. That single decision, made in the silicon, dictates everything that comes after. Okay, so we've got our physical engine. Our brain is sitting there, ready to go. But how do we tell it what to do? This is where we climb up to the next layer of abstraction. We need a language, a set of rules. We need algorithms. An algorithm is really the soul of any piece of software. It's the pure abstract logic. Before you ever write a line of Python or Java, you have an algorithm. It's the essential blueprint, the step-by-step recipe that translates a human idea into a series of commands the machine can actually understand and execute. And the way we express these algorithms comes down to different programming philosophies, what we call paradigms. They're just different ways of thinking. Imperative is like a drill sergeant. Do this, then do that. Object-oriented is like building with digital Legos. You create these little objects that have their own data and behaviors. Functional is all about pure math, trying to avoid changing things. And then there's declarative, which is really cool. You just describe what you want, not how to get it, like asking a database for all users over 30.
So we've climbed from the physical hardware up to the abstract world of logic. But there's one more leap to make, and it's the biggest one yet. What happens when we use these algorithms to build systems that don't just follow our instructions, but actually start to learn on their own? This is where artificial intelligence is born.
You know, AI didn't just appear out of nowhere. Its history has been this wild ride of incredible ambition, and frankly, some major disappointments. Periods called AI winters, where progress just stalled because the problems were so much harder than anyone thought. The deep learning revolution we're living through today was built on decades of work, a shift to new statistical methods, and, crucially, the arrival of powerful hardware like GPUs that could finally run these incredibly complex algorithms.
So what was the big shift that unlocked the AI we have today? It was a complete change in philosophy. Early AI, or symbolic AI, was all about humans trying to handcraft every single rule of intelligence. It was fragile. Modern, statistical AI does the complete opposite. We don't give it the rules. We give it massive amounts of data and let it learn the patterns for itself. It's the old difference between giving someone a fish and teaching them how to fish.
And that brings our entire journey full circle. The AI revolution isn't magic, it's the perfect storm of these three essential pillars coming together at the right time. You need the powerful hardware we started with, you need the sophisticated algorithms we built on top of it, and you need the massive data sets to fuel the whole learning process. You take away any one of those three legs, and the entire structure just collapses.
So we've done it. We've built the stack from silicon all the way up to intelligence. The final step is to ask the really important question. What does this all mean for us? Now that these systems are here, we have to grapple with the profound impact they're having on our society and our future.
And the power of these systems creates ripples that touch every single part of our lives. We're talking about massive economic shifts, both in job automation and the creation of whole new industries. We're dealing with serious social concerns about privacy, algorithmic bias, and what this all means for how we interact. And then you have the really tough ethical challenges of fairness and accountability. These are no longer just academic debates. They're real-world design problems we have to solve.
And that leaves us right here, with this final critical question. The technical journey from a piece of silicon to an artificial intelligence is, without a doubt, one of the greatest engineering feats in human history. The next chapter, the one we're all writing together, will be defined by how we answer this. As we build these increasingly powerful minds, how do we ensure they reflect our highest values? That is the conversation we all need to be having right now.